You've been saying a lot of chemistry examples for assembly theory. What if we zoom out and look at a bigger scale of an object?
Mhm.
Like really complex objects, like humans or living organisms that are made up of millions or billions of other organisms. How do you try to apply assembly theory to that?
At the moment, we should be able to do this to morphology in cells. So we're looking at cell surfaces and really trying to extend further. It's just that, you know, we work so hard to get this paper out and people to start discussing the ideas. And I was, and but it's kind of funny because I think the penny is falling on this. So yeah, so
What's that even? What's it mean for a penny to be?
I mean, no, the penny's dropped, right? Because a lot of people are like, it's rubbish, it's rubbish. You've insulted me, it's wrong. And then, I mean, the paper got published on the 4th of October.
Mm-hmm.
It had 2.3 million engagements on Twitter, right? And it's been downloaded over a few 100,000 times. And someone actually wrote to me and said, this is an example of really bad writing and what not to do. And I was like, if all of my papers got read this much, because that's the objective, if I have a publishing a paper, I want people to read it, I want to write that badly again.
Yeah. I don't know what's the deep insight here about the negativity in the space. I think it's probably the immune system of the scientific community making sure that there's no bullshit that gets published. And then it can overfire, it can do a lot of damage, it can shut down conversations in a way that's not productive.
Go back, I mean, I'll answer your question about the hierarchy in assembly, but let's go back to the perception. People saying the paper was badly written, I mean, of course we could improve it. We could always improve the clarity.
Let's go there before we go to the hierarchy.
Yeah.
It has been criticized quite a bit, the paper. What has been some criticism that you found most powerful? Like, that you can understand, and can you explain it?
The most exciting criticism came from the evolutionary biologists telling me that they thought that origin of life was a solved problem, and I was like, "Whoa, we're really onto something," because it's clearly not. And when you poke them on that, they just said, "No, you don't understand evolution." And I said, "No, I don't think you understand that evolution had to occur before biology, and there's a gap." Mm-hmm. That was really, for me, that misunderstanding, and that did cause an immune response, which was really interesting. The second thing was the fact that physicists were actually really polite, right? Really nice about it. But they just said, we're not really sure about the initial conditions thing, but this is a really big debate that we should certainly get into because, the emergence of life was not encoded in the initial conditions of the universe. Mm-hmm. And it can't, and I think assembly theory shows why it can't be.
I'll say that. Sure. If you could say that again.
The origin of the emergence of life was not and cannot, in principle, be encoded in the initial conditions of the universe.
Just to clarify what I mean by life is like what, high assembly index objects?
Yeah. And this goes back to your favorite subject.
What's that?
Time.
Right. So why? What does time have to do with it?
Probably we can come back to it later, but okay. I think it might be if we have time. Yeah. But I think that I think I now understand how to explain how lots of people got angry with the assembly paper, but also the ramifications of this is how time is fundamental in the universe, and this notion of combinatorial spaces, and there are so many layers on this, but you have to become I think you have to become an intuitionist mathematician, and you have to abandon Platonic mathematics, and also Platonic mathematics has left physics astray. But there's a lot to unpack there, so we can go to the
Platonic mathematics. Okay, hey, it's okay. The evolutionary biologists criticize because the origin of life is understood, and not. It doesn't require an explanation that involves physics.
Yeah,
that's their statement.
Well, I mean, I think they said lots of confusing statements. Basically, I realized the evolutionary biology community that were vocal, and some of them were really rude, really spiteful, and needlessly so, right? Because, look, I didn't. people misunderstand publication as well. Some of the people have said, "How dare this be published in Nature? This is, what a terrible journal." And it really, what I said to people, look, this is a brand new idea that's not only potentially going to change the way we look at biology, it's going to change the way we look at the universe. And everyone's like saying, "How dare you? How dare you be so grandiose?" I'm like, no, this is not hype. We're not like saying we've invented some, I don't know, we've discovered an alien in a closet somewhere just for hype. We genuinely mean this to genuinely have the impact or ask the question. And the way people jumped on that was a really bad precedent for young people who want to actually do something new, because this makes a bold claim. And the chances are that it's not correct. But what I wanted to do is a couple of things. I wanted to make a bold claim that was precise and testable and correctable, not another woolly information in biology argument, information Turing machine, blah, 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 blah. A concrete series of statements that can be falsified and explored, and either the theory could be destroyed or built upon.
Well, what about the criticism of you're just putting a bunch of sexy names on something that's already obvious?
Yeah, that's really good. So the assembly index of a molecule is not obvious. No one had measured it before. And no one has thought to quantify selection, complexity, and copy number before in such a primitive, quantifiable way. I think the nice thing about this paper is a tribute to all the people that understand that biology does something very interesting. Some people call it negentropy. Some people think about, organizational principles, that lots of people were not shocked by the paper because they'd done it before. A lot of the arguments we got, some people said, "Oh, it's rubbish. Oh, by the way, I had this idea 20 years before." I was like, which one? Is it the rubbish part or the really revolutionary part? So this kind of plucked two strings at once. It plucked there is something interesting that biology does, we can see around this, but we haven't quantified yet. And what this is, a first stab at quantifying that. So the fact that people said this is obvious, but it's also so if it's obvious, why have you not done it?
Sure, but there's a few things to say there. One is, this is in part a philosophical framework, because it's not like you can apply this generally to any object in the universe. It's very chemistry focused.
Yeah, well, I think you will be able to. We just haven't got there robustly. So if we can say, let's go up a level. So if we go up from let's go up from molecules to cells, because you jump to people and I jump to emoticons, and both are good, and they will be assembled.
Let's stick with cells, yeah.
So if we go from molecules to assemblies, and let's take a cellular assembly. A nice thing about a cell is you can tell the difference between a eukaryote and a prokaryote, right? The organelles are specialized differently. We then look at the cell surface, and the cell surface has different glycosylation patterns, and these cells will stick together. Now let's go up a level in multicellular creatures. You have cellular differentiation. Now, if you think about how embryos develop, you go all the way back, those cells undergo a differentiation in a causal way that's biomechanically a feedback between the genetics and biomechanics. I think we can use assembly theory to apply to tissue types. We can even apply it to different cell disease types. So that's what we're doing next. But we're trying to walk. The thing is, I'm trying to leap ahead. I want to leap ahead to go, well, we apply it to culture. But clearly, you can apply it to memes and culture. And we've also applied assembly theory to CAs. And not as you think.
Cellular automata, by the way.
Yeah, to cellular automata, not just as you think. Different CA rules were invented by different people at different times. And one of my co-workers, very talented chap, basically was like, "Oh, I can realize that different people had different ideas with different rules, and they copied each other and made slightly different cellular automata rules, and looked at them online." And so he was able to infer an assembly index and copy number of rule whatever doing this thing. But I digress. But it does show you can apply it at a higher scale. So what do we need to do to apply assembly theory to things? We need to agree there's a common set of building blocks. So in a cell, well, in a multicellular creature, you need to look back in time. So there is the initial cell, which the creature is fertilized and then starts to grow. And then there is cell differentiation, and you have to then make that causal chain both on those. So that requires development of the organism in time. Or if you look at the cell surfaces and the cell types, they've got different features on the cell, walls and inside the cell. So we're building up. But obviously, I want a leap to things like emoticons, language, mathematical theorems.
But that's a very large number of steps to get from a molecule to the human brain.
Yeah. And I think they are related, but in hierarchies of emergence, right? Yeah. So you shouldn't compare them. I mean, the assembly index of a human brain, what does that even mean? Well, maybe we can look at the morphology of the human brain, say all human brains have these number of features in common. If they have those number of, and then let's look at a brain in a whale or a dolphin or a chimpanzee or a bird and say, okay, let's look at the assembly indices, number of features in these. And now the copy number is just a number of how many birds are there, how many chimpanzees are there, how many humans are there.
But then you have to discover for that the features that you would be looking for.
Yeah, and that means you need to have some idea of the anatomy.
But is there an automated way to discover features?
I guess so. I mean, and I think this is a good way to apply machine learning and image recognition just to basically characterize things.
So apply compression to it to see what emerges, and then use the features used as part of the compression as the measurement of as the thing that is searched for when you're measuring assembly index and copy number.
And the compression has to be, remember, the assembly universe, which is you have to go from assembly possible to assembly contingent, and that jump from because assembly possible, all possible brains, all possible features all the time. But we know that on the tree of life and also on the lineage of life, going back to Luca, the human brain just didn't spring into existence yesterday. It is a long lineage of brains going all the way back. And so if we could do assembly theory to understand the development, not just in evolutionary history, but in biological development as you grow, we are going to learn something more.
What would be amazing is if you can use assembly theory, this framework, to show the increase in the assembly index associated with, I don't know, cultures or pieces of text like language or images and so on, and illustrate without knowing the data ahead of time, just kind of like you did with NASA, that you're able to demonstrate that it applies in those other contexts. I mean, and that, probably wouldn't at first, and you have to evolve the theory somehow. You have to change it. You have to expand it,
I think so.
But like that, I guess this is, as a paper, a first step in saying, okay, can we create a general framework for measuring complexity of objects, for measuring life, the complexity of living organisms?
Yeah.
That's what this is reaching for.
That is the first step. And also to say, look, we have a way of quantifying selection and evolution in a fairly not mundane, but a fairly mechanical way.
Yeah.
Because before now is, it wasn't the ground truth for it was very subjective. Whereas here we're talking about clean observables, and there's going to be layers on that. I mean, with collaborators right now, we already think we can do assembly theory on language. And not only that, wouldn't it be great if we can, if we can figure out how under pressure language is going to evolve and be more efficient, because you're going to want to transmit things. And again, it's not just about compression. It is about understanding how you can make the most of the architecture you've already built. And I think this is something beautiful that evolution does. We're reusing those architectures. We can't just abandon our evolutionary history. And if you don't want to abandon your evolutionary history, and you know that evolution has been happening, then assembly theory works. And I think that's a key comment I want to make, is that assembly theory is great for understanding when evolution has been used. The next jump is when we go to technology. Because of course, if you take the M3 processor, I haven't bought one yet, I can't justify it, but I want to at some point. The M3 processor arguably is there's quite a lot of features, a quite
Mhm.
large number. The M2 came before it, then the M1, all the way back. You
Mhm.
can apply assembly theory to microprocessor architecture.
Mhm.
It doesn't take a huge leap to see that.
I'm a Linux guy, by the way, so your examples go way over my
Yeah,
head.
well, whatever.
Is that like a fruit company of some sort? I don't even know. Yeah, there's a lot of interesting stuff to ask about language. Like you could look at how would that work? You could look at GPT-1, GPT-2, GPT-3, 3, 5, 4, and try to analyze the kind of language it produces. I mean, that's almost trying to look at assembly index of intelligent systems.
Yeah, I mean, I think the thing about large language models, and this is a whole hobby horse I have at the moment,
Mhm.
is that obviously they're all about the the evidence of evolution in the large language model comes from all the people that produced all the language, and that's really interesting, and all the corrections in the Mechanical Turk, right?
Sure.
Um, and and
But
so
that's part of the history, part of the memory of the system.
exactly. So so it would be really interesting to basically use an assembly-based approach to making language in a hierarchy, right?
Mhm.
I think my guess is that we might be able to build a new type of large language model that uses assembly theory, that it has more understanding of the past and how things were created. Basically, the thing with LLMs is they're like everything, everywhere, all at once, splat,
Mhm.
and make the user happy. So there's not much intelligence in the model. The model is how the human interacts with the model. But wouldn't it be great if we could understand how to embed more intelligence in the system?
What do you mean by intelligence there? Like, you seem to associate intelligence with history
Yeah. Well,
and memory.
I think selection produces intelligence.
You're almost implying that selection is intelligence. No.
Yeah, kind of. I would go out on a limb and say that, but I think it's a little bit more. Human beings have the ability to abstract, and they can break beyond selection, and this is what like Darwinian selection,
Mhm.
because the human being doesn't have to basically do trial and error.
Yeah.
But they can think about it and say, "Oh, that's a bad idea. Won't do that," and then technologies and so on.
So we escaped Darwinian evolution, and now we're on to some other kind of evolution, I guess.
Yeah,
Higher,
yeah,
higher level evolution.
and will assembly theory will measure that as well, right? Because
Yeah.
it's all a lineage.
Okay. Another piece of criticism, or by way of question, is how is assembly theory or maybe assembly index different from Kolmogorov complexity? So for people who don't know, Kolmogorov complexity of an object is the length of a shortest computer program that produces the object as output.
Yeah, I seem to there seems to be a disconnect between the computational approach to this. So yeah, so a
Mhm.
Kolmogorov measure requires a Turing machine,
Mhm.
requires a computer, and that's one thing. And the other thing is, um, assembly theory is supposed to trace the process by which life evolution emerged. Right, there's a main thing there. There are lots of other layers. So Kolmogorov complexity, you can approximate Kolmogorov complexity, but it's not really telling you very much about the actual. It's really telling you about like your data set, compression of your data set,
Sure.
and so that doesn't really help you identify the turtle in this case is the computer.
Mhm.
And so what assembly theory does is I'm going to say. It's a trigger warning for anyone listening who loves complexity theory. I think that we're going to show that AIT is a very important subset of assembly theory, because here's what happens. That I think that assembly theory allows us to build, understand when selection's occurring. Selection produces factories and things. Factories in the end produce computers, and you can go, then algorithmic information theory comes out of that. The frustration I've had with looking at life through this kind of information theory is it doesn't take into account causation. So the main difference between
Yeah.
assembly theory and all these complexity measures is there's no causal chain.
Yeah.
And I think that's the main.
As the causal chain is at the at the core of assembly theory.
Exactly. And if you've got all your data in a computer memory, all the data is the same. You can access it in the same way. You don't care. You just compress it, and you either look at the program runtime or the shortest program. And that, for me, it is absolutely not capturing what its selection does.
But assembly theory looks at objects. It doesn't have information about the object history. It's going to try to infer that history by looking for the shortest history, right? Like
So-
the object doesn't like have a Wikipedia page that goes with it about its history.
I would say it does in a way, and it is fascinating to look at. So you've just got the object, and you have no other information about the object. What assembly theory allows you to do with the object is to, and the word infer is correct. I agree with infer. So you like say, well, that's not the history, but something really interesting comes from this. The shortest path is inferred from the object. That is the worst case scenario if you have no machine to make it. So that tells you about the depth of that object in time. And so what assembly theory allows you to do is, without considering any other circumstances, to say from this object, how deep is this object in time, if we just treat the object as itself without any other constraints. And that's super powerful, because the shortest path then allows you to say, oh, this object wasn't just created randomly, there was a process. And so assembly theory is not meant to, one up AIT or to ignore the factory. It's just to say, hey, there was a factory. And how big was that factory, and how deep in time is it?
But it's still computationally very difficult to compute that history, right, for complex objects.
It is. It becomes harder. But one of the things that's super nice is that it constrains your initial conditions, right?
Sure.
It constrains where you're going to be. So if you take, imagine. So one of the things we're doing right now is applying assembly theory to drug discovery. Now, what everyone's doing right now is taking all the proteins and looking at the proteins and looking at molecules docked with proteins. Why not instead look at the molecules that are involved in interacting with the receptors over time, rather than thinking about and use the molecules that evolve over time as a proxy for how the proteins evolved over time, and then use that to constrain your drug discovery process. You flip the problem 180 and focus on the molecule evolution rather than the protein. And so you can guess in the future what might happen. So you, rather than having to consider all possible molecules, you know where to focus. And that's the same thing if you're looking at in assembly spaces for an object where you don't know the entire history, but you know that in the history of this object, it's not going to have some other motif that it doesn't apply. It doesn't appear in the past.
But just even for the drug discovery point you made, don't you have to simulate all of chemistry to figure out how to come up with constraints?
No,
on the molecules and the.
No,
I mean, I don't know enough about protein.
Well, this is another thing that I think causes, because this paper goes across so many boundaries. So chemists have looked at this and said, this is not correct reaction. It's like, no, it's a graph.
Sure, there's assembly index and shortest path examples here on chemistry.
Yeah. And what you do is you look at the minimal constraints on that graph. Of course, that has some mapping to the synthesis, but actually you don't have to know all of chemistry. You just have to understand. You can build up the constraint space rather nicely. But this is just at the beginning, right? There are so many directions this could go in. And as I said, it could all be wrong, but hopefully it's less wrong.
What about the little criticism I saw of, by way of question, do you consider the different probabilities of each reaction in the chain? So like that there could be different... When you look at a chain of events that led up to the creation of an object, doesn't it matter that some parts in the chain are less likely than others?
No.
It doesn't matter.
No. Well, let's go back. So no, not less likely, but So no. So let's go back to what we're looking at here. So the assembly index is the minimal path that could have created that object probabilistically. So imagine you have all your atoms in a plasma. You got enough energy. You got enough. There's collisions. What is the quickest way you could zip out that molecule with no reaction constraints?
How do you define quickest there then?
It's just basically walk on a random graph.
Yeah.
So we make an assumption that basically the time scale for forming the bonds. So no, I don't want to say that because then it's going to have people obsessing about this point. And your criticism is a really good one. What we're trying to say is like this puts a lower bound on something. Of course, some reactions are less possible than others, but actually, I don't think chemical reactions exist.
Oh boy, what does that mean?
Okay.
Why don't chemical reactions exist?
I'm writing a paper right now that I keep being told I have to finish, and it's called "The Origin of Chemical Reactions," and it merely says that reactivity exists as controlled by the laws of quantum mechanics, and reactions. Chemists put names on reactions, like so you could have like I don't know the Wittig reaction, which is by Wittig. You could have the Suzuki reaction, which is by Suzuki. Now, what are these reactions? So these reactions are constrained by the following. They're constrained by the fact they're on planet Earth, 1G, 298 Kelvin, 1 bar. So these are constraints. They're also constrained by the chemical composition of Earth. Oxygen, availability, all this stuff. And that then allows us to focus in our chemistry. So when a chemist does a reaction, that's a really nice compressed shorthand for constraint application. Glass flask. Pure reagent, temperature, pressure, bomb, control. So, of course, we have bond energies at this. So the bond energies are kind of intrinsic in a vacuum. If you say that, so the bond energy, you have to have a bond, and so for assembly theory to work, you have to have a bond, which means that bond has to give the molecule a certain half-life. So you're probably going to find later on that some bonds are weaker. And that you are going to miss in mass spectrum. When you look at the assembly of some molecules, you're going to miscount the assembly of the molecule because it falls apart too quickly because the bonds just form. But you can solve that with looking at infrared. So when people think about the probability, they're kind of misunderstanding. Assembly theory says nothing about the chemistry, because chemistry is chemistry and their constraints are put in by biology. There was no chemist on the origin of life, unless you believe in the chemist in the sky and they were, it's like Santa Claus. They had a lot of work to do. But chemical reactions do not exist in the constraints that allow chemical transformations to occur do exist.
Okay. So it's constraint application. So there's no chemical reactions. It's all constraint application, which enables the emergence of what's a different word for chemical reaction? Transformation.
Yeah, like a function. It's a function. But I love chemical reactions as a shorthand, and so the chemists don't all go mad. I mean, of course, chemical reactions exist on Earth.
It's a shorthand.
It's a shorthand for all these constraints.
For right. So assuming all these constraints that we've been using for so long, we just assume that that's what was the case in natural language conversation.
Exactly. The grammar of chemistry, of course, emerges in reactions, and we can use them reliably. But I do not think the Wittig reaction is accessible on Venus.
Right. And this is useful to remember, to frame it as constraint application is useful for when you zoom out to the bigger picture of the universe and looking at the chemistry of the universe and then starting to apply assembly theory. Yeah. That's interesting. That's really interesting. But we've also pissed off the chemists now.
Oh, okay. They're pretty happy, but most of them.
No, everybody deep down is happy, I think. They're just sometimes feisty. That's how they show. That's how they have fun.
Everyone is grumpy on some days when you challenge. The problem with this paper is it's almost like I went to a party. It's like used to do this occasionally when I was young. Is go to a meeting and just find a way to offend everyone at the meeting simultaneously. Yeah. Even the factions that don't like each other, they're all unified in their hatred of you, just offending them. This paper, it feels like the person that went to the party and offended everyone simultaneously, so stop fighting with themselves and just focused on this paper.
Maybe just a little insider interesting information. What were the editors of Nature, like what the reviews and so on, how difficult was that process? Because this is a pretty big paper.
Yeah, I mean, when we originally sent the paper, and the editor said um, that this was quite a long process. So we sent the paper, and the editor gave us some feedback and said, I don't think it's that interesting. It's not, or it's hard. It's hard concept. And we asked, and the editor gave us some feedback, and we. And Sarah and I took a year to rewrite the paper.
Was the nature of the feedback very specific on like this part, or was it like what are you guys smoking? What kind of
Yeah,
drug
it
are you
was
taking?
kind of the latter. What are you smoking?
Okay.
And
But polite and there's promise.
yeah. Well, the thing is, the editor was really critical, but in a really professional way.
Yeah.
And I mean, for me, this was the way science should happen. So when it came back, we had too many equations in the paper. If you look at the preprint, there's just equations everywhere, like 23 equations. And when I said to Abhishek, who was the first author, we've got to remove all the equations. But my assembly equation staying in, Abhishek was like, no, we can't. I said, well, look, if we want to explain this to people, there's a real challenge. And so Sarah and I went through I think it was actually 160 versions of the paper, but we got to version 40 or something. We said, right, zero it, start again. So we wrote the whole paper again. We knew the entire...
Amazing.
And we just went bit by bit and said, what is it we want to say? And then we sent the paper in, and to us, we expected it to be rejected and not even go to review. And then we got notification back it had gone to review, and we were like, oh my god, it's so going to get rejected. How's it going to get rejected? Because the first assembly paper that on the mass spec we sent to Nature went through 6 rounds of review and was rejected. Right, and there's by a chemist who just said, I don't believe you, you must be committing fraud. And a long story, probably a boring story, but in this case it went out to review, the comments came back, and the comments were incredibly no, they were very deep comments from all the reviewers. There were but the nice thing was the reviewers were kind of very critical but not dismissive. They were like, oh really? Explain this, explain
That's
this,
great.
explain this, explain this.
Great.
Are you sure it's not Komagolorov? Are you sure it's not this? And we went through, I think, 3 rounds of review pretty quick. And the editor went, yeah, it's in.
Maybe you could just comment on the whole process. You've published some pretty huge papers on all kinds of topics within chemistry and beyond. Some of them have some little spice in them, a little spice of crazy. Like Tom Waits says, I like my town with a little drop of poison. So, it's not a mundane paper. So what's it like psychologically to go through all this process, to keep getting rejected, to get reviews from people that don't get the paper, or all that kind of stuff, just from a question of a scientist? Like what is that like?
It's I think it's I mean, this paper for me kind of, because this wasn't the first time we tried to publish assembly theory at the highest level. The Nature Communications paper we on the mass spec on the idea went to Nature and got rejected. Went through 6 rounds of review and got rejected, and I just was so confused when the chemist said this can't be possible. I do not believe you can measure complexity using mass spec. And also, by the way, molecules, complex molecules can randomly form. And we're like, but look at the data. The data says, and they said, no, we don't believe you. And we went and I just wouldn't give up. The editor in the end was just like the different editors actually, right?
What's behind that never giving up? Is it like when you're sitting there, 10 o'clock in the evening, there's a melancholy feeling that comes over you, and you're like, okay, this is rejection number 5. Or it's not rejection, but maybe it feels like a rejection because the comments are that you totally don't get it. Like, what gives you strength to keep going there?
I don't know. I don't normally get emotional about papers, but it's not about giving up because we want to get it published because we want the glory or anything. It's just like, why don't you understand? And so, what I did, what I would just is try to be as as um, as rational as possible and say, yeah, you didn't like it. Tell me why, and then, um, sorry, give me a second. Silly.
Any part?
Never get emotional about papers normally, but I think what we did, you just compressed like 5 years of angst from this.
So it's been rough.
It's not just rough. It's like it happened. I came up with the assembly equation, remote from Sarah in Arizona and the people at SFI. I felt like I was a mad person, like, the guy depicted in a Beautiful Mind, who was just like, not the actual genius part, but just the gibberish.
Yeah.
Because I kept writing expanded, and I have no mathematical ability at all. And I was making these mathematical expansions where I kept seeing the same motif again. I was like, I think this is a copy number. The same string is coming again and again and again. I couldn't do the math. Mm-hmm. And then I realized the copy number fell out of the equation and everything collapsed down. I was like, oh, that works, kind of. So we submitted the paper. And then when it was almost accepted, right, the mass spec one, and it was astrobiologist said, great. A mass spectroscopist said, great. And the chemist went, nonsense, like biggest pile of nonsense ever, fraud, And I was like, but why fraud? Mm-hmm. And they just said, just because. Mm-hmm. And I was like, well, and I could not convince the editor in this case. The editor was just so pissed off because they see it as like a kind of you're wasting my time. And I would not give up. I went and dissected, all the parts. And I think, although, I got upset about it, which is kind of embarrassing actually, but I guess.
Beautiful.
But it was just trying to understand why they didn't like it. So there were part of me was like really devastated. And a part of me was super excited because I'm like, they can't tell me why I'm wrong. And this kind of goes back to, when I was at school, I was in a kind of learning difficulties class, and I kept going to the teacher and say, what do I do today to prove I'm smart? And they were like, nothing, you can't. I was like, give me a job, give me something to do. Mm-hmm. Give me a job to do, something to do as we, and I kind of felt like that a bit when I was arguing with and not arguing, there was no ad hominem. I wasn't telling the editor they were idiots or anything like this, or the reviewers. I kept it strictly like factual. And all I did is I just kept knocking it down bit by bit by bit by bit by bit. It was ultimately rejected and it got published elsewhere. And then the actual experimental data. So this is kind of, in this paper, the experimental justification was already published. Mm-hmm. So when we did this one and we went through the versions and then we sent it in, and in the end it just got accepted, we were like, well, that's kind of cool, right? This is kind of like, some days you have, the student, sorry, the first author was like, I can't believe it got accepted. I was like, nor am I. Mm-hmm. But it's great. It's like, it's good. Mm-hmm. And then when the paper was published, I was not expecting the backlash. I was expecting computational, no, actually, I was just expecting one person who'd been trolling me for a while about it, just to carry on trolling. Mm-hmm. But I didn't expect the backlash. And then I wrote to the editor and apologized. And the editor was like, what are you apologizing for? It was a great paper. Mm-hmm. Of course it's going to get backlash. You said some controversial stuff, mm-hmm. but it's awesome. And so,
well, I think it's a beautiful story of perseverance, and the backlash is just a negative word for discourse, which I think is beautiful.
I think you, as I said to, when it got accepted and people were saying, we're kind of like hacking on it. And I was like, papers are not gold medals. Mm-hmm. The reason I wanted to publish that paper in Nature is because it says, hey, there's something before biological evolution. You have to have that if you're not a creationist, by the way. Mm-hmm. This is an approach. First time someone has put a concrete mechanism, a concrete quantification, and what comes next you're pushing on is a mechanism. Mm-hmm. And that's what we need to get to, is an autocatalytic sets, self-replicating molecules, some other features that come in. And the fact that this paper has been so discussed, for me, is a dream come true. Like, it doesn't get better than that. If you can't accept a few people hating it, And the nice thing is, the thing that really makes me happy is that no one has attacked the actual physical content. Like you can measure the assembly index, you can measure selection now. So either that's right or either that's helpful or unhelpful. If it's unhelpful, this paper will sink down and no one will use it again. If it's helpful, it'll help people build scaffold on it, and we'll start to converge to a new paradigm. So I think that that's the thing that I wanted to see, my colleagues, authors, collaborators, and people who are like, you've just published this paper, you're a chemist, why have you done this? Like, who are you to be doing evolutionary theory? Like, well, I don't know. I mean, sorry, did I need to
Who's anyone to do anything? Well, I'm glad you did. Let me just, before coming back to origin of life and these kinds of questions, you mentioned learning difficulties. I didn't know about this. So what was it like?
I wasn't very good at school, right?
This is when you were very young?
Yeah. Well, but in primary school, my handwriting was really poor, and apparently I couldn't read, and my mathematics was very poor. So they just said, this is a problem. They identified it. My parents kind of at the time were confused because I was busy taking things apart, buying electronic junk from a shop, trying to build computers and things. And then once I got out of, when I was, I think, about the major transition in my stupidity, like, everyone thought I wasn't that stupid when basically everyone thought I was faking. I like stuff and I was faking wanting to be it. So I always wanted to be a scientist. Mm-hmm. So 5, 6, 7 years old, I'd be a scientist, take things apart. And everyone's like, yeah, this guy wants to be a scientist, but he's an idiot. Mm-hmm. and so everyone was really confused, I think, at first, that I wasn't smarter than I, was claiming to be. Mm-hmm. And then I just basically didn't do well in the test. And I went down and down and down and down. And then, and I was kind of like, this is really embarrassing. I really like maths, and everyone says I can't do it. Mm-hmm. I really like kind of physics and chemistry and all that in science, and people say you can't read and write. And so I found myself in a learning difficulties class at the end of primary school and the beginning of secondary school. In the UK, secondary school is like 11, 12 years old. Mm-hmm. And I remember being put in the remedial class, and the remedial class was basically full of three types of people. There were people that had quite violent, right? Mm-hmm. And there were people who couldn't speak English, mm-hmm. and there were people that really had learning difficulties. So, the one thing I can objectively remember was, I could read. I like reading. I read a lot. But something in me, I'm a bit of a rebel. I refused to read what I was told to read. And I found it difficult to read individual words in the way they were told. But anyway, I got caught one day teaching someone else to read. And they said, okay, we don't understand this. I always knew what to be a scientist, but I didn't really know what that meant. And I realized you had to go to university. And I thought, I can just go to university to take curious people. I'm like, no. You need to have these. You have to be able to enter these exams to get this grade point average. And the fact is, the exams you've been entered into, you're just going to get C, D, or E. You can't even get A, B, or C, right? Mm-hmm. These are the UK GCSEs. I was like, oh, shit. And I said, can you just put me into the higher exams? I said, no, you're going to fail. There's no chance. So my father kind of intervened and said, just let him go in the exams. And they said, he's definitely going to fail. It's a waste of time, waste of money. And he said, well, what if we paid? So they said, well, okay. So he didn't actually have to pay. He had to pay if I failed. Mm-hmm. So I took the exams and passed them, fortunately. I didn't get the top grades, but I got into A-levels. But then that also kind of limited what I could do at A-levels. I wasn't allowed to do A-level maths.
So, what do you mean you weren't allowed to?
Because I had such a bad math grade from my GCSE, I only had a C. Mm-hmm. But they wouldn't let me go into the ABC for maths because of some kind of coursework requirement back then. So the top grade I could have got was a C, so C, D, or E. So I got a C, and they let me do kind of AS level maths, which is this half intermediate, but get to go to university. But in the end, I liked chemistry. I had a good chemistry teacher, so in the end, I got to university to do chemistry.
So through that kind of process, I think for kids in that situation, it's easy to start believing that you're not. Well, how do I put it? That you're stupid, and basically give up. That you're just not good at math. You're not good at school. So this is by way of advice for people, for interesting people, for interesting young kids right now experiencing the same thing. Where was the place? What was the source of you not giving up there?
I have no idea, other than um, I I really like not understanding stuff. For me, when I not understand something, I didn't understand. Feel like I didn't understand anything. But back then, I was so. I remember when I was like, I don't know, I tried to build a laser when I was like 8,
Hmm.
and I thought, how hard could it be? Like, and I basically. I was going to build a CO. I was going to build a CO2 laser, and I was like, right. I think I need some partially coated mirrors.
Hmm.
I need some carbon dioxide, and I need a high voltage.
Hmm.
So and I was like, I didn't have and I was so stupid, right? I was kind of so embarrassed. To make enough CO2, I actually set a fire
Hmm.
and try to filter the flame
Oh, nice.
to
Well, that's an
trap
idea.
enough CO2.
Yeah.
And I was like, it completely failed, and I burnt half the garage down.
Hmm.
So my parents were not very happy about that. But so that was one thing. I was like, I really like first principle thinking, and so you know. So I remember being super curious and being determined to find answers. And so the kind of when people give advice about this, well, I ask for advice about this. I don't really have that much advice other than don't give up. And one of the things I try to do as a chemistry professor in my group is I hire people that I think that, I'm kind of, who am I, if they're persistent enough, who am I to deny them the chance? Because, people gave me a chance and I was able to do stuff.
Do you believe in yourself, essentially?
I love being around smart people, and I love confusing smart people. And when I'm confusing smart people, not by stealing their wallets and hiding it somewhere, but if I can confuse smart people, that is the one piece of hope that I might be doing something interesting.
Oh, that's quite brilliant. Like as a gradient to optimize.
Yeah.
Hang out with smart people and confuse them.
Yeah.
And the more confusing it is, the more there's something there.
And as long as they're not telling you just a complete idiot and they give you different reasons.
Yeah.
And I mean, if everyone, because like with assembly theory and people said, oh, it's wrong. And I was like, why? And they're like, and no one could give me a consistent reason. They said, oh, because it's been done before, or it's just Kolmogorov, or it's just that, and the other. So I think the thing that I like to do is, and in academia, it's hard, right? Because people are critical. But I mean, the criticism, I mean, although I got kind of upset about it earlier, which is kind of silly, but not silly, because obviously it's hard work being on your own or with a team spatially separated, like during lockdown, and try to keep everyone on board and be, have some faith that I've always wanted to have a new idea. And so, I like a new idea and I want to nurture it as long as possible. And if someone can give me actionable criticism, that's why I think I was trying to say earlier when I was kind of like stuck for words, give me actionable criticism. It's wrong. Okay, why is it wrong? You say, oh, it doesn't, your equation's incorrect for this, or your method is wrong. And then so what I try and do is get enough criticism from people to then triangulate and go back. And I've been very fortunate in my life that I've got great colleagues, great collaborators, funders, mentors, and people that will take the time to say, you're wrong because. And then what I have to do is integrate the wrongness and go, oh, cool. Maybe I can fix that. And I think criticism is really good. People have a go at me because I'm really critical. I'm like, but I'm not criticizing, you as a person. I'm just criticizing the idea and trying to make it better and say, well, what about this? And, and sometimes I'm kind of, my filters are kind of, truncated in some ways. I'm just like, that's wrong. What to do this? And people are like, oh my God, you just told me you destroyed my life's work. I'm like, well, relax. No, I'm just like, let's make it better. And I think that we don't do that enough because we're we're either personally critical, which isn't helpful, or we don't give any criticism at all because we're too scared.
Yeah, I've seen you be pretty aggressively critical, but it's every time I've seen it, it's the idea, not the person.
I'm sure I make mistakes in that. I mean, I argue lots with lots. I mean, I argue lots with Sarah, and she's like kind of shocked. I've argued with Yasha in the past, and he's like, "You're just making Yasha Buck," and you're just making that up. I'm like, no, not quite, but kind of.
Yeah.